In today's video, we're going to be looking at 11.2b and the other half of part C as well. So this is looking at hypothesis testing when we don't know that population standard deviation. We only have a sample standard deviation that we can use to estimate the population standard deviation. Because of that, we can't use that z value, that z-score, that we used as our test statistic before, because remember, if we don't know our population standard deviation, we cannot find that z-score because it's within the formula for the z transformation. So instead, what we're going to do is use that sample standard deviation as an estimate for that population standard deviation in that formula. But if you remember back to when we did confidence intervals, that actually gave us something called a student's t-distribution. So we actually end up with a t-value rather than a z-value, okay? But the actual formulation of this is almost exactly the same as what we've done before. It's just that now our test statistic is going to look very slightly different. I'll quickly write down what that test statistic is, and then we can talk about it. I'll take that out for a second. We'll write it as that. Okay. So this is the value that is going to be used as our test statistic. Now, remember, a t-value that we get is only dependent on two things. Number one is an area, just like when you do inverse norm in a calculator to find a z-value, it will ask for an area. That is the probability that is to the left of that z-value, okay? Exactly the same when we do t-values, okay? For a t-value, the area is always the area to the left of the value under that curve, okay? So it asks for the area, and it also asks for the degrees of freedom. So a t-value or a t-score depends on, number one, the area under the curve to the left of the value, and secondly, it's the degrees of freedom. And the degrees of freedom is just the sample size minus 1. Okay, if you remember that from when we did our confidence intervals. So that's the two things that this thing will depend on. Okay, we use this much more than when we do the z-test for hypothesis testing. We actually use a t-test much more. The reason is because if you think about the way that we formulated that, when we did a z-test, you had to know that population standard deviation, because instead of an s that we have in this formula, when we found z, it asked for the population standard deviation sigma. The reason that we conduct a hypothesis test normally in this case is because we want to know whether the population mean is what we think it is. We are testing what the population mean is, whether it's the value that we think it is, or from some sample data that we've accumulated, is it actually bigger, smaller, or just different than what we initially thought. Okay, so we are testing that population mean because we're not entirely sure what it is. Well, if we're not entirely sure what our population mean is, we're hardly going to know what our population standard deviation is. So in most real world examples, this is the test that we actually use. A t-test is used far more than a z-test because you normally don't know the population standard deviation. You only know the standard deviation of the sample. So we just use that S value for the sample standard deviation instead of using the population standard deviation. Let's do an example. This is actually in the notes. If you go to the Google Drive, you will actually see the two examples that I'm going through in 11.2b notes. So if you want to follow along on the Google Drive notes, I would do that. The first example says that a researcher has designed a questionnaire she believes will take an average of 35 minutes to complete. Suppose the random samples of 20 employees finds that the mean time to take the test is 29 minutes with a standard deviation of 8 minutes. Determine if there is sufficient evidence to conclude that the mean time of the new test differs from the old one. Assume the population is normally distributed and conduct the test at the 0.05 level. Okay, so it's set up in very much the same way. The only difference is that we now have a sample standard deviation as opposed to a population standard deviation. We're going to go through the same steps that we did last time. It's just that our test statistic is now slightly different. So step 1 was to find our null and alternative hypotheses. We actually want to see what we're testing. Okay, so in this hypothesis test, okay, they think that the population mean is 35 minutes, but they have taken a sample and they have seen that the mean time of the sample is 29 minutes. But all they are saying here is that if you look, they just want to see if the mean time of the new test differs from the old one. They don't want to see if it's less than or greater than, even though in the sample the test was actually quicker than the population mean, so the mean time that they thought it would take to take this test. But even though that mean is smaller, they're just looking at whether the mean is different from what they initially thought. So the null hypothesis, as we said, it's always that the mean is equal to what they thought it was. You always have equality when you do the null hypothesis. For the alternative hypothesis, they're testing just whether the mean is different from what they thought it was, because they've got some sample data that suggests otherwise. Okay, so we've got our null and alternative hypotheses. The next step, that was step 1. Step 2 is just to find the significance level. And that is always given in the problem. So find the significance level alpha. And in this case, they want to conduct the test at the 0.05 level. So alpha is 0.05. Okay, that means that we want to reject our null hypothesis 5% of the time. Okay, the other 95%, we want to accept that null hypothesis for what it is. Okay. Step 3 is to find the test statistic. Okay, so we want to find the test statistic. Now in this case, as I said, we have been given a sample standard deviation, not a population standard deviation. If they gave you a population standard deviation, you're going to use a z-value. If they give you a sample standard deviation, you use this t-value. So we know that we have a sample standard deviation. So this is the formula that we will use for our test statistic. All this is doing is taking a t-score, a t-value, for the sample mean that we have been given. Very much the same. It's the same formula that we used when we did these confidence intervals and we had to find a t-value. It's very much the same, okay? So we know that our sample mean is 29. The population mean was 35. It's the value that we initially thought it was. The sample standard deviation was 8 and the sample size was 20. If you work that out, your value is negative 3.35. Okay, so that is our test statistic value. The next step is that we need to find a critical value, because then we can compare our critical value to our test statistic, and that is what's going to determine whether we reject or fail to reject that null hypothesis. So step 4 is to find the critical value. Critical value is always found depending on what your significance level is, okay? It always depends on that significance level alpha. When you do this, okay, a student's t distribution looks very, very much like a normal distribution. And the greater your sample size is, the more it's going to look like a normal distribution, okay? So let's say it's actually slightly flatter than a normal distribution, but it looks very much the same, okay? We want, in this case, we have a two-sided alternative hypothesis, okay? which means it's two-tailed. We know that our significance level is 0.05. Because we have a two-tailed test at the 0.05 significance level, we know that we need to have 0.025 on either tail. So at the lower end, we want 0.025, and at the upper end, we want 0.025. If you had a one-tailed test, whether it be left or right-tailed, you would put that whole 0.05 in either the left or the right tail. But we know that we have a two-tailed test here, as we have a two-sided alternative hypothesis with a does not equal. So because of that, we're going to end up with two different critical values. Okay, we're going to have one here and one here. And the area under the curve to the left of this t value, we'll call it t1, is 0.025. And the area to the right of this t value, we'll call it t2, is also 0.025. Okay, so if our test statistic falls either to the right of this t value or to the left of this t value, it's going to fall in that intolerance zone. It's going to fall within that 5% of the time that we want to reject our null hypothesis. Okay, so if we've got 5% between the two of those areas, we know that we're going to have 95% in the middle. Okay, and if our t value, if our test statistic was to fall in this range, we know that we would fail to reject our null hypothesis. Okay, and we're going to accept it for what it is, and we're going to say that the mean is still 35. Okay, so we've got to find T1 and T2. Now, the way that you do this is to use inverse T on your calculator. So when you found a Z value, you used inverse norm. To find a T value, you use inverse T. Okay, it's found in exactly the same place on your calculator. So if you go to second and vars and scroll down, it's option 4. And you will see it will ask you for two things. The first thing is the area. The second thing is the degrees of freedom. The area, as always, is the area to the left of the t value that you want. So it's the area under the curve to the left of the t value. So to find T1, it's going to be inverse T of 0.025. And the degrees of freedom, okay, it's always the sample size minus 1, which in this case would be 20 minus 1, which is 19, okay? If you do that, you should find that the t value is negative 2.093, okay? And in the same way, if you do this for T2, okay, T2, the area to the left of it is going to be 0.025 plus 0.95, which is 0.975. And again, it's got the same degrees of freedom, which would give you the positive of that value, 2.093. Okay. Now we want to see where our test statistic lies. Okay. So if we look at our test statistic, it was negative 3.35. So let's look at where that is on our diagram. So T1 was negative 2.093. T2 was 2.093. We had for our test statistic negative 3.35, which means that our t value, our test statistic, lies somewhere over here, okay? It's going to be to the left of negative 2.093, okay? So our t value falls here, which means it's in that intolerance zone, which means that we must have to reject that null hypothesis. So step 5 is to determine, step 5, determine whether to reject H0 or not. Okay, so in this case, because t is equal to negative 3.35, falls in that intolerance zone, okay? So the area where we know that we want to reject our null hypothesis, that 5% of the time, we reject the null hypothesis. Okay. So we know that we want to reject our null hypothesis in favour of the alternative. So that tells us always go back for step 6, always put it back in terms of the original problem. So in this case, your conclusion would be that the new test actually does not take 35 minutes. Now, we don't know from our test whether it takes less than or greater than 35 minutes because we've only tested that it's different than 35 minutes. Okay, so even though our sample suggested it was less than, we can't determine that right now from the hypothesis test that we have conducted. Okay, so all we can say in terms of the problem is because we reject our null hypothesis, it means that the new test does not take 35 minutes. It actually just takes a different time than 35 minutes. Okay, so always relate it back to the original problem. Okay. So the next question that we have, I'm going to do another problem here that is a one-tailed test. And it says that an engineer designed a valve that will regulate water pressure on a car engine. The engineer designed the valve such that it would produce a mean pressure of 5.5 pounds per square inch. It is believed the value performs above specifications. Okay, so far what we have in this problem is we have been given that we think the mean is 5.5 and they want to conduct a hypothesis test to see whether this valve performs above specifications. The valve was tested on 18 engines and the mean pressure was 5.6 pounds per square inch with standard deviation of 0.08. Assume the population is normally distributed and a level of significance of 0.01 is used. Okay, so we want to test this. So we know that, given the information, our null hypothesis is that the mean is 5.5, that it hasn't changed. Now we want to test whether this valve, given, this should be HA, our alternative hypothesis, we want to test whether the valve actually performs above specifications because we have some sample data that suggests it. Okay, so we want to see if in fact our mean is greater than 5.5. Okay, so we have our null and alternative hypothesis and we want to test this. Okay. Now, I'm going to do this the shorter way. Again, you can do it the way that we just did, okay? In this case, you are dealing with a one-tailed test, okay? Your significance level is 0.01, okay? And you are dealing with a one-tailed test. So what you would be doing here is, again, finding your test statistic using a t-value where you take the sample mean minus the population mean of 5.5 divided by that sample standard deviation of 0.8 over the square root of the sample size, which was 18. Okay, so you could go ahead and find that test statistic. You can then find the critical value. In this case, it is a one-tailed test, and it is actually right-tailed. Okay, because you have a greater than, it means it's right-tailed, so your tail is going to be over here. So again, if you draw a sketch of this, okay, this time it is one-tailed. Your tail is going to be at the right because you've got a greater than. And your significance level of 0.01 will all be in that one tail. So it means that your area under here is 0.01. Your area here is 0.99 for a total of 1. And then this would be your critical value. We'll call it T1. So again, you can figure out T1. Okay, T1 in this case would be inverse T. Okay. Your area to the left of it is 0.99. Your degrees of freedom, again, is the sample size minus 1, which would be 17. Okay, so you can go ahead, find that critical value. You can find your test statistic, and you can see whether your test statistic falls in this danger zone over here, that intolerance zone, where we would reject our null hypothesis. Okay, that would be the long way of doing it. But as always, there is a shorter way of doing it, which is on your calculator using t-test, okay? It's right where you found z-test in the last section. So if you go to stat, go across to tests, so you go to stat and tests, and the second option is t-test, Now, in this case, they have given you statistics. If they had given you sample data, you would have to put your sample data in a list and you would use the input of data, okay, once you put that information in a list. But right now, they have given you sample statistics. They've given you a sample mean and a sample standard deviation. So you can go down and put the information in. So mu0 is the mean, the population mean that we thought we had. So the population mean that we are considering right now is 5.5. Okay. The sample mean, the mean that they got from their sample, was 5.6. Okay. Then your SX is the sample standard deviation. Okay, SX is the sample standard deviation, which was 0.8. N is the sample size, which is 18. The next line, they ask you whether you have a two-tailed or a left or right-tailed. They ask you, is your alternative hypothesis a does not equal to, a less than, or a greater than? In our case, it's a greater than. Okay, so make sure you have that one selected, and then you can calculate. Then it will give you all of this information. Okay, so it will give you that test statistic, that t value. So if they ask you for the test statistic, it is on that second line down. So that t value that they have on that screen is just where they have calculated the sample mean minus the population mean over the sample standard deviation divided by the square root of the sample size. It has figured that out for you, okay? So that t value is what they would compare to this critical value to determine whether you would reject or fail to reject. So you have your t value. The next line down is that p value, okay? The p value that we've talked about before, and I'm going to come back to that in a minute. And again, they give you your sample mean, sample standard deviation, and the sample size that we talked about, whichever your sample size is from the problem, okay? So what we have been given here, okay, this is exactly the same as last time. Your p-value is roughly 0.301 in this problem, okay? What you do is you compare it to your significance level. So exactly the same as last time. And what this does, that p-value tells you the probability that you will have a test statistic as extreme or more extreme than the one you have. So it is the probability, in this case you've got t is 0.53, okay? What this p-value tells you is the probability that you have a test statistic that is at least as extreme as this value, okay? Now, in this case, 0.053, bearing in mind that a t-value of 0 is right in the middle. T of 0.53 is actually pretty close to this middle 0 value, okay? So we can probably see, even from the diagram, okay, if 0.53 was roughly here, okay, you can see that this thing is pretty close to 0, so we're ultimately going to fail to reject. You can tell this also from the p-value, comparing the p-value to alpha, okay? If p is less than alpha, so if p is less than alpha, we will reject the null hypothesis, okay? Because what that means, if you've got a p-value that is really, really small and less than alpha, it means that the probability of that test statistic, or having a more extreme value than that test statistic, is going to be really, really small. And it means that it's going to have an area that is smaller than alpha. And it's going to lie somewhere over here, because that area is going to be smaller than that alpha area that we had, okay? So our alpha area here is 0.01. But if you had a p-value that was smaller than that, it would mean that you had an area that was even smaller. So it would mean that the value that is associated with that, so this t-value here, it would mean that that value would lie in that danger zone, that intolerance zone where we would reject our null hypothesis. But if p is greater than alpha, which is what we have in this case, p is actually much greater than alpha, we will fail to reject that null hypothesis. We are going to accept it for what it is. So in this case, we have p greater than alpha. P is 0.301, alpha is 0.01. So we're going to fail to reject H0. So we think that our mean, our population mean, is still going to be 5.5. Our sample mean of 5.6 is not far enough away from that population mean for us to really be worried about it changing. Okay, we still think that that mean is 5.5. Okay, as I said, this is very, very similar to what we did in 11.2a. The only difference is now we have this t value as opposed to a z value, okay, for our test statistic. And remember that t values, if you have to go ahead and find that critical value that you're going to use to compare to your test statistic, if you have to find that critical value, okay, remember to use inverse t. And inverse t depends not only on the area like a z value did, but it also depends on the degrees of freedom. So if they do ask you to find a critical value, bear that in mind, okay? But the rest of this is very much the same as 11.2a, okay? Go ahead and try this, and again, read through the notes for these examples on the Google Drive. It's under 11.2b and c. So go ahead and read those notes because that will help you as you go through this video as well. If you've got any questions, please let me know, because I know this isn't the easiest chapter, but once you get a hang of it, it will be super simple and it will help you out as we go through the rest of it. In 11.3, we go through the same thing, but for population proportions as our null and alternative hypotheses instead of means, but the rest of it is very much the same as well. Okay. If you've got any questions, please let me know, and I will see you in the next video.